Now, this is just a diagram to show you how. Now, we talked about changing electric field produces a changing magnetic field. The changing magnetic field produces a changing electric field. Now, when you talk about electromagnetic waves, this is what we talk about. We have E and B, perpendicular to each other.
Yeah.
They drive each other all the way through. So in this case, let's say if it's propagating in the direction shown, right? And if you point your fingers in the direction of E, right? And if you curl your fingers, then you get B. And this is how basically, waves travel, which is equations 3 and 4, I believe. So when we talk about magnetic fields, I want to ask you, so we talked briefly about magnetic fields, but if you're talking about magnetic fields, the first thing that comes to your head is probably a magnet, right? Because I think as kids, I remember as a kid, I was fascinated when...
I too.
Because, the thing I couldn't understand was, you have two magnets. Okay, they suddenly get... And then you turn one around, suddenly they're repairing. So people thought it was... And, you could not see it, right? But it's there. There's something there.
Yeah.
Right? So when you talk about magnetic fields, I think you cannot escape what we call permanent magnets, right? I think they're used in so many commercial applications. I mean, forget about sensors. They're used in, I don't know, a whole lot of, fridge magnets and all these things. So many commercial applications, but also used in a lot of sensing applications. Now, this is one way of creating magnetic fields. The other way, as we talked about, was Ampere, right? He said if you have a wire, you give it a current, you will create a magnetic field around it. Now, so here I have, if you want to look at the current, it's going this way. So your magnetic field, if you use the right-hand rule, then it will be in this direction. But your electron flow is obviously in the opposite direction, right? So you should not use the electron flow. And if you have a magnetic compass there,
it will align to
that magnetic field direction. Now, so now we've talked about the equations of magnetic fields, but have you ever seen a magnetic field, electromagnetic field, electric field, or a magnetic field, or an electromagnetic field?
The field that we have talked about is not visible to our...
Right.
Yeah. Maybe it is good. Otherwise, we'll be seeing all the magnetic field, electromagnetic field, not the... So I think by design, our eyes are
not designed not to see
those
magnetic fields. So they're invisible, but we know they're there because, for example, you take a magnet, you sense the force, right? The power. So if we are to know, for example, the strength of a magnetic field or strength of an electric field, how can we do that?
We will have to somehow measure it.
Somehow measure. So I guess this is where electromagnetic sensors come into the picture, right? So we have all these fields. We know they're there. There are equations that describe these fields, but we also need to somehow measure these fields, and this is where our electromagnetic sensors come in. Now again, electromagnetic sensors, they will either exploit electromagnetic or electromagnetic fields, and to get more information about something of interest to us. Depends on the application, on the use case. Right. So if you're talking about magnetic sensors, there's a lot. See this, Boby. See, these are some of the most widely used magnetic sensors.
Okay.
So you can see there are a lot of different types of sensors, and the other thing is they use magnetic fields, but they use them in different ways. They are designed in different ways to somehow exploit these magnetic fields. Now here, what you see here is the strength of the magnetic field. Or rather, magnetic...
Or the range?
A value, right? So the value, a range of magnetic field that these sensors can detect. Now this GMN is geomagnetic noise, and E is, as you said, the Earth's magnetic field. Now, what you can see here is certain sensors.
Some of them have got limited range.
Yes, and some of them, like the search coil here, for example, right? You can see it's wrong range. Pretty much covers
Entire range.
entire range. Now, that can be an advantage. That can also be a disadvantage. Why do you think that's a disadvantage?
It is sensitive to everything in there.
Sensitive to everything, right? If you're trying to measure, I don't know, picotesla, it's also sensitive to millitesla. So that might totally cover or mask what you're trying to measure. Now, you also have something like a Hall effect sensor, and you say that's a magnetodiode, right? Very small range.
Millitesla.
Millitesla. So they can probably be used for specific applications where you're working with magnetic fields in the millitesla range, but nothing less than that. You also have this arrow is going this way.
So you were mentioning about some Fluxgate earlier. What is its range?
So this Fluxgate is shown here. That range is it's as good as a search coil, but not as it cannot go down to picotesla.
Nanotesla can measure.
Nanotesla can measure, and so can a search coil. But you see, it's squid magnetometer here.
Oh, so it can go to.
Why is the arrow this way?
It can go to smaller and smaller values.
Smaller and smaller values. So, and out of all these sensors, it seems like that's the only sensor that can, measure very, very small magnetic field.
Maybe 10 power minus 15 or so?
Yeah, something. Pico is what? Pico is
12.
12, right? So 15 is femtotesla. Yeah, femtotesla. So, but you'll see, it can measure very. So if you look at squid magnetometers, right? So another thing, interesting thing about these magnetic sensors are their size, right? So certain sensors like Hall effect sensors or this GMR, AMR.
What is GMR?
So remember in the first slide we said we are going to talk about 4 different types of sensors.
Okay.
Right. So GMR is called Giant Magneto Resistive sensor.
Okay.
Right. And these
that comes under the MR.
Right. So here we can see kind of 2. Actually, magnetic tunnel junction has also a very similar kind of operation, but that comes under magneto resistive sensors. Now, the magneto resistive sensors and the Hall effect sensors, you can actually make them very small.
Yeah, IC form.
But let's say a squid sensor.
I heard this requires some -degree temperature to operate, and heavy.
Yes. So squid can measure very small magnetic fields, but it's limited in the sense that it requires I think some helium or nitrogen cooling. Operation.
So maybe for some specific scientific studies,
yes,
could be used, but not for a commercial product.
No, and it's also quite big. So definitely in situ, there's no way you can take it to places, right?
Yeah.
Whereas if you talk about Hall effect and magneto resistive type sensors, you can make portable sensors using those sensors, right? So here we have some sensors and we have the noise at certain frequencies.
Oh, squid has got very low noise.
And
that's why it is able to resolve very small quantity.
I believe squid. So, and it's, very consistent, right? Across, let's say 1 hertz to all the way to about 1000 hertz. That noise
level is very low.
Whereas if you look at an inductive sensor, you see, it changes, right, at high frequencies.
Yeah.
I mean, it works well at high frequencies than lower frequencies. Fluxgate again comes down at high frequencies. NMR and
So in this, MR has got the highest
noise.
That means it's bad. As far as
Well,
resolution is concerned.
As far as resolution is concerned, I believe, it's not as good as. Definitely not. I mean, nothing's as good as.
We cannot resolve quantities smaller than this noise using the sensor.
Yes. And also, it seems to be.
It may have very good sensitivity. That is different.
Yes. And it also, changes according to frequency. Right. So as you said, it probably has good sensitivity, but when it comes to, I guess, accuracy.
Or resolution. Smallest quantity it can resolve.
Yes. Might not be.
It's limited.
Might not be high as the other ones. Just another way of looking at the different types of sensors here. And again, this is the range. Okay. But it shows the different applications these sensors can be used in.
Okay, nice.
Right? So, for example, if you look at navigation here, right?
It's like a compass.
It's like compass. And navigation is very important, right? So, actually, when it comes to like things like autonomous vehicles and I think space and ships, right? Critical, right? Otherwise, you might get lost. And again, here it also shows the sensors that can be used in navigation. But similarly, there are so many different applications like non-destructive testing.
What is non-destructive testing?
So non-destructive testing is basically you somehow use electromagnetic methods where you don't really touch the sensor. It's non-invasive. You're not really.
You mean the test object?
Yes, the test object. You're not necessarily touching it, or it could be like minimally invasive. But so what I'm trying to say is, you will not modify the object of interest in any way.
So, for example, if you have a piece of metal made out of some process, and you wanted to find out is there some fault inside, you will test it without cut opening it.
Yes. Yes. Somehow you should be able to use.
So, for example, if that is sensitive to magnetic field, then you may expose it to a magnetic field and see is there an unexpected change.
Anomaly or change. Yes.
Got it.
But you're not trying to modify that in any way. Rotation sensing. I think angle sensors. And that I think a lot of sensors can be used for that, right? For angle sensing. But you see, SQUID, you only have this. Actually, image. I'm pretty sure it's something to do with this is tomography. I'm not sure what image is. Maybe it's something to do. I'm sure it's a medical application. But as you said, limited application.
What is it called?
MEG.
So this, I think, magnetic encephalography maybe.
Okay. Okay. And then do you know what that does? So
probably looking at the
brain.
Sorry. Change in the magnetic field.
So that means we are talking about very small fields.
It will be very, very small.
Correct. So what else? So, interesting thing we talked about.
So actually wide spectrum of applications.
Wide spectrum applications, but
from medical to automotive.
Absolutely. So used in a lot of different
navigation to anything.
So you could even say crucial to many of these applications.
Yes.
Right. See, we talked about the Earth's magnetic field, right? But not many sensors can detect that. Here you can see
Hall effect can sense.
Hall effect. Well, according to this, maybe no, but I think Hall effect.
Hall effect can
sense. Yes.
I have used it.
But again, here, but search coil again. Looks like a sensor that you can use for anything. See, it's across.
Yeah. So, but maybe we'll have to design depending on the range that you are sensing.
Yeah, and the size.
So for electromagnetic field, what is that the image suggest?
This image suggests either AMR, Fluxgate, nuclear precision, optical, surge coil.
Okay. So then that means, see, electromagnetic field 50 to 60 microtesla is probably the change that they are going to sense is maybe for, let's say, the ore. I mean,
Again, ore.
For to find mining field.
Yeah.
For example, if such small variations in the magnetic field that they are going to look at,
right,
then it needs better sensitivity.
Yes.
Sensitivity and this good resolution.
Rather than the resolution.
Yeah.
Yes.
Hall effect will just say north and south you can detect.
Okay. I see what you're trying to say.
Yes. You may not be able to say how many nanotesla change. It will not show.
Right. Yeah. So if you have a large area with ores, for example, it will be very sensitive to that.
Yeah.
But it will not be able to say the different areas.
Yeah.
Yes.
So if something like that is there will be minute change in the magnetic field, which the Hall sensor will not be able to.
Yes. Which is why maybe here they have AMR.
Fluxgate. Yeah. Fluxgate may be a better option.
Yes. That case. But a lot of applications. And this is just a picture just to show supply chain and key players. Some of the students might be interested in sensor manufacturers and some of the systems they use. Automotive sensors, there are so many magnetic sensors there. And I'm sure you heard of companies like Infineon and NXP, TDK, right? Sensitech, right? They have an automotive focus. So magnetic field sensors in automation. In the automotive field. You also have e-compass, which is basically navigation, right? Again, NXP is there, Bosch, Dyna, Yamaha, interesting, Alps, right? And you also have, our phones have navigation too, right? So, then industrial applications, Honeywell, Murata, again, Sensitech, right? So lots of different companies, and you see, they're used in many different systems, right? Automotive, cars, phones, navigation equipment. Here we have, I don't know, what is this? It's like a motor. But Schneider, Siemens, Honeywell, but industrial applications. So, electromagnetic sensors are very useful.
It's good to study.
So, I think it's good to start, right? So I think that's the last lecture, slide. So here we talked about surge coils, wide range, and that is the first sensor we'll study.